So what we're going to do now is we're going to prove the division algorithm. So again, what are we looking to prove? If we have an a and b, where b is strictly greater than 0, and a and b, of course, are integers, then there exist unique integers, and that's the key part here, they're unique integers, q and r, such that a can be decomposed into a product and a sum, so a is equal to b times q plus r, where r is going to be bounded, so it's going to be greater than or equal to 0, but strictly less than b. So we're going to break this proof up into really three main parts. So the first thing that I want to do is I'm going to fix a and b. So a and b are going to be integers, so in the set z, with the condition that b has to be strictly greater than 0. Okay. So the first part that we want to do is we want to show that there exists a q and r such that a is equal to bq plus r with, right now, we're going to relax the condition that it has to be bounded above by, it has to be strictly less than b. We're just going to have to say at this point in time that r is going to be greater than or equal to 0. The second part of this is we are going to show that r has to be strictly less than b. But for now, we just want to be able to show that there does in fact exist, for any given a and b, where b holds the condition that it's strictly greater than 0, that there is going to be a q and an r such that r is going to be at least positive. All right, so like I said, the first thing that we want to do is we want to be able to show that a q and r does in fact exist. So let's let x be an element of z. So what we're going to do is just to prove that there is in fact, for again any given a and b, a q and an r that exists with r going to be greater than or equal to 0. So a is equal to bq plus r. I can rewrite this as, let's move bq to the other side. So a minus bq is equal to r. So what I first want to do is, again, I want to be able to show that there's a q and an r, and we'll pick very specific ones, but for now, let's leave this very general. So I'm going to replace q with a placeholder. I'm just going to put an x in there. So a minus bx, and instead of an r at this point in time, I'm just going to use the condition, because r has to be greater than or equal to 0. I'm just going to say this a minus bx has to be greater than or equal to 0. Now, one thing to note, the result of this a minus bx, this we can think of as, this would be the remainder if we went through this process and we didn't have any sort of conditions on the fact that r had to be bounded in this sort of way. So we can think of this as a minus bx again as remainders. So let's let S be a set of all integers of the form a minus bx, where x, again, is an integer and a minus bx greater than or equal to 0. So let's just think of what S is going to be. S is going to be a set of these remainders. So we've been able to find an x and a remainder such that, again, that remainder is going to be positive. So I'm building S to be a set of positive integers or positive remainders overall. Because, again, I want to tie this into the last idea that we had, which was the well-ordering axiom, that if I have this positive set of integers, there's going to be a smallest element inside of there, and that's going to be key for us. But right now, what we want to be able to do is, again, the idea is we want to show that there is a q and an r that does in fact exist for this. We want to be able to show that S is in fact non-empty, because as soon as there's an element inside of S, then that means there does in fact exist this x and this r which potentially could be our Q and an R. We'll get to that in a little bit of time here. So we first want to show that it's not empty. So for there to be a Q and R, S cannot be empty. Let's put a comma there. So we need to find an X where A minus BX greater than or equal to 0. Because as soon as I have that X, then I have that remainder from there. All right, let's bring this up a little bit. So let's start off with the condition that we do know. We know that B is strictly greater than 0. But we can say a little bit more than that. We can say that B is greater than or equal to 1 because it has to be an integer. It can't be 0. Thus, the smallest it possibly can be is 1. Now, what I'm going to do is I'm going to multiply on the left and right-hand side of this inequality the absolute value of A. So A does exist. It's an integer. It could be positive. It could be negative. We're going to take the absolute value of that, and again, with the absolute value, that makes it positive. So when I multiply it on either side of this inequality, it's not going to change the direction of the inequality. So B times the absolute value of A is greater than or equal to the absolute value of A, because I'm just doing that multiplied by 1, still the absolute value of A. Now, one of the properties that we have with absolute values is we can say the absolute value of A is greater than or equal to negative A. So if I rewrite this last line, greater than or equal to negative A, well, one of the things I can do is I can move this negative A to the other side. So I'm going to have A plus B absolute value of A is greater than or equal to 0. Now this looks very, very close to what we're dealing with because we want A minus BX to be greater than or equal to 0, but right now we have that pesky plus sign, so it's not in exactly the right form. All right, so we wanted to be able to find an X such that this exists. This A minus BX is greater than or equal to 0, and we kind of have a guess right now that it has something to do with the absolute value of A. Well, let's let X be equal to the negative of the absolute value of A. And now let's plug this X in, and clearly X is in fact an integer because A is an integer. We take the absolute value of that, it's still an integer. We make it negative, again, still an integer, that hasn't changed. So we found an X that's an integer, but does this X in fact work? Well, if we plug it into this A minus BX, and now we're going to replace X with knowing that it is negative the absolute value of A. So this is A minus B times negative absolute value of A. Negative and negative make positive, so A plus B absolute value of X. And we know from above here, this is greater than or equal to 0. So that means with this choice of X, which is in fact an integer, when we plug it in, we are going to get a result or a remainder that is in fact going to be positive. So what does this mean for us? Well, this means that this set is not empty. So A minus BX is an element of S, so there is some remainder when X is equal to the negative, the absolute value of A. Now, are we saying that's the only case? No, but we just needed one because all we were doing is showing that this set is in fact non-empty. All right, so we have a set S, it's non-empty, it's a set of remainders. Now what we're going to do is we are going to pick a very specific Q and a very specific R. We'll pick the R first. So since S is a set of positive integers, by the well-ordering axiom, and let's try and move this up a little bit here. There we go. So by this well-ordering axiom, comma, S, must have a smallest element. So let's let R be that smallest element. So remember, S is kind of made up of all these remainders. All of these remainders are positive, and we're going to say we're going to pick the smallest one, and we're going to call that R. So R is equal to this A minus BX for some X. We know that X has to exist because, again, R wouldn't be in there if the X didn't exist. So for this specific X, we'll call this Q. So we picked R to be the smallest, and its respective X, we're calling that Q. So we can say R is equal to A minus BQ instead of X, or if I just rearrange this a little, I'm going to say A is equal to BQ plus R, and the condition on R right now is R is greater than or equal to 0. All right, so we're kind of heading in the right direction at this point in time. We've been able to find a Q and an R where R is greater than or equal to 0. What we want to now show, this 2 remaining steps, is firstly that R is actually in fact going to be less than, strictly less than B. And then the last step of this is showing that these 2 integers, this Q and R, is specifically unique. So let's bring this up a little bit more, but I do want to keep this line because this line is going to be important for us. So the second outcome here is show R is strictly less than B. Now how we do this is we're going to assume this is not true. So we're assuming it's not true, so we're saying R is greater than or equal to B. And we're going to show that there has to be a contradiction in here. Okay, so with R greater than or equal to B, I can bring the B to the other side, and this says R minus B is greater than or equal to 0. Well, how does this help us? Well, as I said above, we're going to need this little bit of information. R, we could write this as A minus BQ. So let's do that. Let's do this substitution in. So instead of R, I'm going to have A minus, actually I'll write R minus B is equal to, I'm going to replace this R with A minus BQ minus that remaining B. So notice here my second and third term both have a B. I can factor that out. And this leaves me with A minus B times Q plus 1. Now Q plus 1, Q was an integer. Has to be an integer because, again, that's the conditions of this. So if I have an integer, I add 1 to that. That's also going to be an element of Z. And we know that R minus B, based upon this assumption, is greater than or equal to 0. So that means this R minus B is an element of our set S. Now this is where the problem comes into play. Think about this for a second. Where is the problem in this? Pause the video if you want. But here's the thing. There is the initial condition on B. We know B is strictly greater than 0. So this implies if B is strictly greater than 0, then R minus B is strictly less than R. So R minus B, we're saying that if all of this is true, assuming that R is greater than or equal to B, that means R minus B has to be an element in S, and R minus B is smaller than R. But that's the contradiction, because once we pick that element R from our set S originally, we pick the smallest element inside of there. So R minus B can't be inside of there because that would say there was a smaller element than the smallest element. That makes no sense. So that doesn't work for us. So this is a contradiction. And it's a contradiction since R is the smallest element. Okay, so where does that leave us with the proof at this point? Well, we still have A, which is equal to BQ plus R, and now we've shown that R is greater than or equal to 0 and strictly less than B. So the last thing that we have to show here is in fact that these two integers are in fact unique. And that one's actually not too bad to prove. Again, we're going to do it in exactly the same way. We're going to assume that it's not true. So step 3, show uniqueness. And we do that by assuming not true. So assuming it's not unique. So if it's not unique, I still have my A, which is equal to BQ plus R, where R is greater than or equal to 0, but strictly less than B. And if it's not unique, then A is also equal to BQ sub 1. So there's another Q plus R sub 1 and another R, where, again, 0 less than or equal to R sub 1 less than B. All right, so what I'm going to do here is I'm going to change this first inequality. I'm going to multiply every part here by -1. So it's negative multiplying, so I'm flipping the sides of the inequalities. So what I get here is I get negative b less than negative r less than or equal to 0. And I'm going to leave the second one alone. So this is still 0 less than or equal to r sub 1 less than b. And what I'm going to do is I'm going to add these two inequalities together. If I add these together, I'm going to get negative b is strictly less than r1 minus r, which is strictly less than b. Okay, so at this point we can ask the question, well, how is this helping? Well, it hasn't helped just yet, but I want to replace this r1 minus r with something. Now, how we're going to do that is we're going to use this condition here that we have these two ways of decomposing a. So since they're both equal to a, well, then I should be able to set them equal to one another. So what I'm going to do is I'm going to take BQ plus R, and this is going to be equal to BQ sub 1 plus R sub 1. My B's and my Q's to one side, my R's to the other side. So this is BQ minus BQ sub 1 is equal to R1 minus R. And we can factor out the B's on the left-hand side. So this is B times Q minus Q1 is equal to R1 minus R. Now notice this is exactly what we have over here. So now I can do a substitution. Now I can say that negative B is less than B times Q minus Q1, which is less than B. Now B we know is a positive integer. So I can divide both sides of this, or all three terms of this inequality, by b, and it's not going to change the direction of the inequality. So this leaves me with -1 less than q minus q1 less than 1. Now q and q1 are both integers, so if I subtract two integers, it's still going to be an integer. So this is telling me this q minus q1 has to be an integer in between -1 and 1, but can't be -1 and 1. Well, there's only one positive integer, or there's only one integer that's in there, and that's 0. So this tells us that q minus q1 is equal to 0, or that q is equal to q1. All right, so we've shown at this point in time that at least for the q's are the same. Now we're going to show the same for the r's. So jumping back over to here, I'm going to use this information that q minus q1 is equal to 0. So this gives me b times 0, I'll do this over here, b times 0 is equal to r1 minus r, b times 0 is 0, r1 minus r, which tells me that r is equal to r1. There we go. So we assumed it wasn't in fact unique, but in this case it is unique. They are the same. Q is equal to q1 and r is equal to r1. So that's the proof right there, folks. The next video, we're going to jump into some examples of this, or exercises of this. That's a better way of saying it. We'll see you then.